Welcome to Basics Revisited. Today we study rational numbers from the basic concept of real numbers all the way to competitive exam problems. We will cover rational and irrational numbers, their properties, rationalization, and plotting on the number line. If you find this helpful, please like and subscribe to Basics Revisited for more concept building videos. Every number that can be placed on a number line is called a real number. Real numbers are made of two groups, rational numbers and irrational numbers. Natural numbers are the counting numbers 1, 2, 3, 4, 5, and so on. They are always positive. Whole numbers include natural numbers plus 0, 0, 1, 2, 3, 4, and so on. Integers include all positive numbers, negative numbers, and 0, -3, -2, -1, 0, 1, 2, 3. Rational numbers are all numbers that can be written in the form p over q, where p and q are integers and q is not 0. Irrational numbers are numbers that cannot be written as p over q, for example, root 2 pi and e. A rational number is any number that can be written in the form p over q, where p and q are integers and q is not equal to 0. Every integer is rational. -3 equals -3 over 1, 0 equals 0 over 1, 7 equals 7 over 1. They all fit the p over q form. Every fraction with integer numerator and non-zero denominator is rational. For example, 3 over 4, -5 over 7, and 22 over 7. Terminating decimals are rational. 0.5 equals 1 over 2, 0.75 equals 3 over 4, 3.125 equals 25 over 8. Non-terminating repeating decimals are also rational. 0.333 repeating equals 1 over 3. 0.142857 repeating equals 1 over 7. Now let us understand how to convert a decimal number into the p over q form. There are two types: terminating decimals and repeating decimals. We handle each differently. Type 1 terminating decimal. Step 1. Write the decimal as a fraction over a power of 10. For 0.75, we write 75 over 100. Step 2. Simplify the fraction by dividing numerator and denominator by their highest common factor. HCF of 75 and 100 is 25, so 75 over 100 simplifies to 3 over 4. More examples. 0.5 equals 5 over 10, which simplifies to 1 over 2. And 3.125 equals 3125 over 1000, which simplifies to 25 over 8. Type 2 repeating decimal. Step 1. Let x equal 0.333 repeating. Call this equation 1. Step 2. Since one digit repeats, multiply by 10. So 10x equals 3.333 repeating. Call this equation 2. Step 3. Subtract equation 1 from equation 2. The repeating part cancels out. We get 9x equals 3. Step 4. Solve for x. X equals 3 over 9, which simplifies to 1 over 3. Another example, 0.272727 repeating. Let x equal 0.2727, then 100x equals 27.2727, subtracting 99x equals 27. So x equals 27 over 99, which simplifies to 3 over 11. Here is the key rule for choosing your multiplier when converting repeating decimals to fractions. Case A: if one digit repeats, multiply by 10. For 0.7 repeating, 10x equals 7.7 repeating, subtracting 9x equals 7. Answer: 7 over 9. Case B: if two digits repeat, multiply by 100. For 0.141414 repeating, 100x equals 14.1414, subtracting 99x equals 14. Answer: 14 over 99. Case C: mixed decimal, 0.47 with 7 repeating. Set x equals 0.4777, then 10x equals 4.777 and 100x equals 47.777, subtracting 90x equals 43. Answer: 43 over 90. Case D: 0.36 with 6 repeating. X equals 0.3666, 10x equals 3.666, 100x equals 36.666, subtracting 90x equals 33. Simplify. X equals 33 over 90 equals 11 over 30. An irrational number cannot be expressed as p over q for any integers p and q. Its decimal expansion is non-terminating and non-repeating. Root 2 equals 1.41421356 and the digits never end and never repeat. This was proved irrational by Pythagoras. Root 3 equals 1.73205. Root 5 equals 2.23606. Root 7 equals 2.64575. All non-terminating, non-repeating. Pi equals 3.14159265 and E equals 2.718281882 are famous irrational numbers that appear throughout mathematics. Note carefully, root 4 equals 2, which is rational. Root 9 equals 3, which is rational. Only roots of non-perfect squares are irrational. Let us now prove that root 2 is irrational, step by step using proof by contradiction. Step 1. Assume root 2 is rational, then root 2 equals p over q, where p and q are integers, q is not 0, and the fraction is in its lowest terms, meaning HCF of p and q equals 1. Step 2. Square both sides. 2 equals p squared over q squared. So p squared equals 2q squared. This means p squared is even. Since the square of an odd number is always odd, p itself must be even. Step 3. Since p is even, write p equals 2k for some integer k. Substitute into p squared equals 2q squared. We get 4k squared equals 2q squared. Simplify, q squared equals 2k squared. So q squared is even, and therefore q must also be even. Step 4. Both P and Q are even. This means their HCF is at least 2, but we assumed HCF equals 1. This is a contradiction. Therefore, our original assumption was false. Root 2 cannot be written as P over Q. Root 2 is irrational. Proof complete. Let us now understand the important difference between a fraction and a rational number. A fraction is the ratio of two positive whole numbers. It is written as a over b, where a and b are positive integers and b is not zero. Fractions cannot have a negative numerator or a negative denominator. For example, 3 over 4 is a fraction, but negative 3 over 4 is not a fraction, it is a rational number. The pi diagram shows 3 over 4. The whole pi is divided into 4 equal parts, and 3 parts are shaded. All counts are positive. A rational number, on the other hand, allows any integers positive or negative in numerator and denominator. So every fraction is a rational number, but every rational number is not necessarily a fraction. And remember, root 2 over 3 is a fraction in form, but it is not a rational number because root 2 is not an integer. Property. The sum or difference of a rational number and an irrational number is always irrational. If r is rational and x is irrational, then r plus x and r minus x are both irrational. Proof by contradiction. Suppose r plus x equals q, a rational number, then x equals q minus r, but rational minus rational is rational. This contradicts x being irrational, so r plus x must be irrational. Examples: 3 plus root 2 equals 4.4142. Irrational. 5 minus root 3 equals 3.2679. Irrational. Note: rational plus rational is always rational. 1/2 plus 1/3 equals 5/6. Always rational. Property. The product or quotient of a non-zero rational number and an irrational number is always irrational. If r is a non-zero rational and x is irrational, then r times x and r divided by x are both irrational. Examples: 2 times root 3 equals 2 root 3. Irrational. 1/3 times root 5 equals root 5 over 3. Irrational. Important exception: 0 times root 2 equals 0, which is rational. 0 times anything equals 0, so the rule only applies when the rational number is non-zero. Division examples: 6 divided by root 2 equals 6 over root 2 equals 3 root 2. Irrational. Root 5 divided by 3 is irrational. What happens when we multiply two irrational numbers? The result can be rational or irrational. It depends on which irrationals you use. Product can be rational. Root 2 times root 2 equals 2. Rational. Root 3 times root 3 equals 3. Rational. Root 2 times root 8 equals root 16 equals 4. Rational. product can be irrational. Root 2 times root 3 equals root 6. Irrational. Root 5 times root 7 equals root 35. Irrational. Division can be rational. Root 8 divided by root 2 equals root 4 equals 2. Rational. Root 18 divided by root 2 equals root 9 equals 3. Rational. Division can be irrational. Root 6 divided by root 2 equals root 3. Irrational. Root 10 divided by root 3 equals root of 10 over 3. Irrational. We never leave an irrational number in the denominator. Rationalizing the denominator means removing the surd from below by multiplying carefully. Step 1. Write the expression 1 over root 2. Step 2. Multiply numerator and denominator by root 2. 1 times root 2 over root 2 times root 2 equals root 2 over 2. Step 3. Since root 2 times root 2 equals 2, the final answer is root 2 over 2, approximately 0.7071. More examples. 3 over root 5 equals 3 root 5 over 5. 6 over root 3 equals 2 root 3. To rationalize 1 over a plus root b, we use the conjugate. The conjugate of a plus root b is a minus root b. When multiplied together, they give a squared minus b irrational number. Step 1. Write the expression 1 over 3 plus root 2. Step 2. Multiply numerator and denominator by the conjugate 3 minus root 2. Step 3. The denominator becomes 3 squared minus root 2 squared. That is 9 minus 2 equals 7. Note carefully, this uses the identity a squared minus b squared where b equals root 2. So b squared equals 2, not just b. Step 4. Final answer 3 minus root 2, all over 7. Another example, 1 over root 5 plus root 3, multiply by root 5 minus root 3. Denominator becomes 5 minus 3 equals 2. Answer, root 5 minus root 3 over 2. Type 1. Simplify root 3 plus root 2 over root 3 minus root 2. Multiply by root 3 plus root 2 on top and bottom. The result is root 3 plus root 2 squared over 1 equals 5 plus 2 root 6. Type 1. Simplify root 3 plus root 2 over root 3 minus root 2. Multiply by root 3 plus root 2 on top and bottom. The result is root 3 plus root 2 squared over 1 equals 5 plus 2 root 6. Type 2. If x equals 3 plus 2 root 2, find x plus 1 over x. Rationalize 1 over x equals 3 minus 2 root 2. Adding x plus 1 over x equals 3 plus 2 root 2 plus 3 minus 2 root 2 equals 6. Type 3. 1 over root 2 plus root 3 plus root 5. Group has root 2 plus root 3 and root 5 separately. Multiply by the conjugate in 2 steps to fully rationalize. Key identity to remember. A plus b times a minus b equals a squared minus b squared. This is the engine behind all conjugate rationalization. Every irrational number has a precise, exact location on the number line. We use the Pythagorean theorem to construct these positions geometrically with a compass. Core idea: a right triangle with legs A and B has hypotenuse equal to root of a squared plus b squared. Legs 1 and 1 give root 2. Legs root 2 and 1 give root 3. Legs root 3 and 1 give root 4 equals 2. To plot root 2, draw a right triangle with both legs equal to 1 unit. The hypotenuse equals root 2. Use a compass to swing this length from the origin onto the number line. To plot root 5, draw a right triangle with legs 2 and 1. Hypotenuse equals root of 4 plus 1 equals root 5. Transfer to number line using compass. Look at this diagram. O is the origin. We draw OA equal to 1 unit along the x-axis. Then we draw AB equal to 1 unit perpendicular at A. Look at this diagram. O is the origin. We draw OA equal to 1 unit along the x-axis. Then we draw AB equal to 1 unit perpendicular at A. AB equals root of 1 squared plus 1 squared equals root 2. Now open the compass to length OD. Keeping the compass at O, swing the arc downward until it meets the number line. That point is exactly root 2. This diagram shows the spiral of Theodorus. Starting at origin O, we build a chain of right-angled triangles. Each triangle uses the previous hypotenuse as one leg and adds a new perpendicular leg of 1 unit. Triangle 1 has legs 1 and 1 giving hypotenuse root 2. Triangle 2 uses root 2 and 1 giving root 3. Triangle 3 uses root 3 and 1 giving root 4 equals 2. Triangle 4 gives root 5. Triangle 5 gives root 6. Triangle 6 gives root 7. The dashed lines show the legs of each triangle. The solid lines show the hypotenuse. The curved arcs sweep each hypotenuse length from O directly onto the number line below. The blinking circles mark the exact positions of root 2, root 3, root 5, and root 7 on the number line. Practice questions for Class 8 and Class 9. Question 1. Is 0.6 repeating rational? Let x equal 0.666 repeating. 10x equals 6.666 repeating. Subtracting. 9x equals 6. So x equals 2 over 3. Yes, it is rational. Question 2. Express 0.47 with 7 repeating as p over q. Let x equal 0.4777 repeating. 10x equals 4.777. 100x equals 47.77. Subtracting. 90x equals 43. So x equals 43 over 90. Question 3. Find two irrational numbers between 2 and 3. Root 5 is approximately 2.236 and root 7 is approximately 2.646. Both lie strictly between 2 and 3. Question 4. Rational is 4 over 3 plus root 5. Multiply by 3 minus root 5 on top and bottom. Denominator becomes 9 minus 5 equals 4. Answer. 4 times 3 minus root 5 over 4 equals 3 minus root 5. Practice questions for Class 10 level. Question 5. Simplify root 5 plus root 3 over root 5 minus root 3. Multiply by root 5 plus root 3 over root 5 plus root 3. Denominator becomes 5 minus 3 equals 2. Numerator becomes root 5 plus root 3 squared equals 8 plus 2 root 15. Answer 4 plus root 15. Question 6. If x equals 2 plus root 3, find x squared plus 1 over x squared. First, 1 over x equals 2 minus root 3, then x plus 1 over x equals 4. Squaring x squared plus 2 plus 1 over x squared equals 16. So x squared plus 1 over x squared equals 14. Now let us prove that root 2 plus root 3 is irrational, step by step. Step 1. Assume root 2 plus root 3 is rational. Call it R, where R equals P over Q, a rational number. Step 2. Isolate 1/3. Write root 3 equals R minus root 2. Square both sides. We get 3 equals R squared minus 2R root 2 plus 2. Step 3. Rearrange to isolate root 2. 2R root 2 equals R squared plus 2 minus 3 equals R squared minus 1. So root 2 equals R squared minus 1 all over 2R. Step 4. The right side is R squared minus 1 over 2R. Since R is rational and 2R is not 0, this entire expression is rational, so root 2 would be rational. But root 2 is known to be irrational. Contradiction. Therefore our assumption was wrong. Root 2 plus root 3 is irrational. Proof complete. Competitive level questions. Question 8. If U equals 1 over root 2 plus 1, find a plus 1 over a. Rational is a. Multiply by root 2 minus 1 over root 2 minus 1. A equals root 2 minus 1. Then 1 over U equals root 2 plus 1. So a plus 1 over U equals root 2 minus 1 plus root 2 plus 1 equals 2 root 2. Question 9. Simplify 1 over 1 plus root 2 plus 1 over root 2 plus root 3 plus 1 over root 3 plus root 4. Each term rationalizes as root 2 minus 1, then root 3 minus root 2, then root 4 minus root 3. Adding these gives a telescoping sum. Root 4 minus 1 equals 2 minus 1 equals 1. Question 10. Find rational A and B if 3 plus root 5 over 3 minus root 5 equals A plus B root 5. Rational is the left side. Multiply by 3 plus root 5 over 3 plus root 5. Denominator becomes 9 minus 5 equals 4. Numerator becomes 3 plus root 5 squared equals 14 plus 6 root 5. So the expression equals 14 plus 6 root 5 over 4 equals 7 over 2 plus 3 over 2 root 5. Therefore U equals 7 over 2 and B equals 3 over 2. Five key rules you must never forget. Rule 1. A rational decimal either terminates or repeats. If a decimal is non-terminating and non-repeating, it is always irrational. Rule 2. Rational plus or minus irrational equals irrational always. Rational times or divided by irrational equals irrational, unless the rational is 0. Rule 3. Irrational times irrational can go either way. Root 2 times root 2 is rational. Root 2 times root 3 is irrational. You cannot assume the result without checking. Rule 4. To rational is 1 over a plus root b. Multiply by the conjugate a minus root b. Use the identity a plus b times a minus b equals a squared minus b squared. Rule 5. To plot root n on the number line, build a right triangle using Pythagoras such that the hypotenuse equals root n. Then transfer the length to the number line using the compass.